In chapter 4.7, we study inverse trigonometric functions. That's right, each one of our trig functions has an inverse, right? More specifically, we're going to be talking about inverse sine, inverse cosine, and inverse tangent functions. Back in chapter 1.9, we studied inverse functions. Well, what does it mean for functions to be inverses of each other? We said the function denoted f inverse of x, notice f with a little -1 here, is the inverse function of f of x if for every ordered pair a comma b that exists in f of x, there is the ordered pair b comma a in f inverse of x. All right, what that meant is that inverse functions were related in that every single x and y coordinate flip-flopped. That meant that the domain of f inverse of x was equal to the range of f of x, and the range of f inverse is equal to the domain of f of x. Now, not every single function had an inverse. In order for a function to have an inverse, it must be one-to-one, meaning that the function must pass the horizontal line test. Graphically speaking, because the domain of f inverse is equal to the range of f, and the range of f inverse is equal to the domain of f, the graphs of inverse functions are reflections of each other over the line y equals x. So here I have a graph of some function f of x. If this is the line y equals x that I've just drawn in here, I take f of x, I reflect it over the line y equals x. That means I'm switching all my x and y coordinates. Right? That gives us the graph of our inverse function. Similarly, here I have a graph of another function. We call it g of x. The inverse, well, I would take that graph, reflect it over the line y equals x, and there I have the shape of g inverse of x. So that's what our graphical relationship between inverse functions is. And you might recall the process for finding inverse functions. Well, we started off, we interchanged the roles of x and y. Wherever we saw a y, we plugged in an x, and wherever we saw an x, we plugged in a y. So in this case, we would have x is equal to the cubed root of 10 plus 2y, and then we proceeded to solve for y using different inverse operations. Like in this case, if we wanted to isolate y, the first thing we would have to do is cube both sides of the equation. All right, why did we cube both sides? Because cubing is the inverse operation of taking a cubed root. That left us with x cubed is equal to 10 plus 2y. Next, we would subtract 10 from both sides of the equation. We subtracted 10 from both sides of the equation because subtracting 10 is the inverse operation of adding 10. And finally, to get the inverse function written y as a function of x, we would divide by 2. We divided both sides of the equation by 2 because dividing by 2 is the inverse operation of multiplying by 2. Inverse operations undo each other. To undo this multiplication of 2, we divide by 2. That gave us x cubed minus 10 divided by 2 is equal to y. There is my inverse function, and using the notation, we would have f inverse of x, if we simplify it out a little bit, would be x cubed divided by 2 minus 5. And graphically speaking, this is the shape of our graph of f of x. We take that graph, we reflect it over the line y equals x, and that gave us our inverse function. Okay, so a good review of inverses. Now let's take that and apply it to our trig functions, starting with our sine function. Here we have the graph of y equals sine of x. And does this function have an inverse? Well, as is, no, it does not. It does not pass the horizontal line test. Notice if I were to draw a horizontal line, I would have multiple intersection points. Can we, however, restrict the domain of the function so that it does have an inverse? In other words, can we only look at particular x values so that it does pass the horizontal line test? Yes. All right. And if we restrict it to values of x between negative pi over 2 and positive pi over 2, that would be this portion of the graph. Now our function is one-to-one. It passes the horizontal line test. Therefore, sine has an inverse on this interval. All right, so graphically, we can reflect our graph of y equals sine of x, this portion of our sine graph, over the line y equals x, and that will give us the graph of our inverse sine function. All right, there we have the graph of y equals arc sine of x, or y equals inverse sine of x. Notice that there are two separate notations. They mean the exact same thing. Okay, y equals arc sine of x, or y equals inverse sine. Get familiar with both. You will see both notations used. One thing to be very, very clear here, this minus 1, this is not an exponent, all right? That doesn't mean to the negative 1 power. That means the inverse function of sine. Okay, now, a couple important things that we need to see here. One is the domain of this function. Well, the domain of our inverse sine function is going to be from -1 to 1. Notice that that matches with the range of our original sine function. The range of y equals the sine of x is -1 to 1. The range of inverse sine is from -pi/2 to pi/2. And that corresponds to our restricted domain, the domain where we restricted our sine function, -pi/2 to pi/2. So the domain of sine becomes the range of inverse sine. And finally, we say by definition now, y equals the inverse sine of x if and only if x equals the sine of y. All right. What this is saying, these two expressions are identical. Think about our original function. We started off with the function y equals the sine of x. To find the inverse algebraically, we would interchange the roles of x and y. That gives me x is equal to the sine of y. Notice that that is the inverse. That's what we see here. X is equal to the sine of y. And the only reason we don't like this notation is because we always like our functions written y as a function of x. So what would we have to do to isolate y? Well, algebraically, all right, to undo taking the sine of something, you have to do the inverse operation of taking sine. And the inverse operation of taking sine is inverse sine. Notice that if we take the inverse side of the left-hand side of the equation and the inverse sine of the right-hand side of the equation, well, we get the inverse sine of x is equal to inverse operations. They are going to cancel each other out, and we are left with y. All right, y equals the inverse sine of x, and x is equal to the sine of y. Those two expressions are actually identical. All right, we like this one, y equals inverse sine of x, because we have y written as a function of x. Okay, let's see if we can't do the same thing with our cosine function now. So here I have a graph of y equals the cosine of x. We have this nice cosine wave. Does the function y equal cosine of x have an inverse? Well, as is, it does not. It fails to pass the horizontal line test. If I draw a horizontal line, I get multiple intersection points. However, can we restrict the domain of the function so that it does have an inverse, so that it does pass the horizontal line test? And the answer to that question is yes. If we look at this function on the interval from 0 to pi, all right, so that's this portion of the graph alone, now the function is 1 to 1, and it does have an inverse on that interval. So what we can do, we take that graph, we reflect it over the line y equals x, and that gives us the graph of our inverse cosine function. All right, here we have y equals arc cosine of x, y equals inverse cosine of x. Again, two different notations that mean the exact same thing. This -1 is not an exponent. That means inverse cosine, the inverse operation of cosine. All right, so there's our graph. The domain of this function, the domain of arc cosine x, is -1 to 1. Notice that that is the range of our original cosine function. The range of inverse cosine is from 0 to pi, and that range corresponds with our restricted domain of our cosine function. Again, we had to restrict the domain of cosine to values between 0 and pi. because we restricted the domain of cosine, those values become the range of inverse cosine. And finally, we say y equals the inverse cosine of f if and only if x is equal to the cosine of y. All right, two different ways to say the exact same thing. And algebraically, again, if we start with our original function, y equals the cosine of x, to find the inverse of this function, we interchange the roles of x and y. X is equal to the cosine of y. This is the inverse function. However, we want to isolate y. In order to isolate y, we have to do the inverse operation of taking the cosine. The inverse operation of taking cosine is to take the inverse cosine. The inverse cosine of the left-hand side is equal to the inverse cosine of the right-hand side of the equation. We get the inverse cosine of x is equal to y. Again, notice inverse operations, they cancel each other out, leaving us with y. So y equals the inverse cosine of x is the same expression as x equals cosine of y, just written in a different manner. Again, we like being able to isolate y. And lastly, let's look at inverse tangent. Okay, here we have the graph of y equals the tangent of x. Does the function y equals tan of x have an inverse? Well, no, it does not pass the horizontal line test. If I were to draw a horizontal line, I'd have multiple intersection points. The function is not one-to-one, therefore it does not have an inverse. But can we restrict the domain of the function so that it does have an inverse? Yes, absolutely. If we look at this tangent function on the interval from negative pi over 2 to positive pi over 2, all right, that would be this region right here. Now my function does have an inverse. Now notice these endpoints have parentheses. They're not included. And the reason being is that at negative pi over 2 and positive pi over 2, we have these vertical asymptotes on our tangent function. Okay, so these values of x, the endpoints, are not defined. All right, so now that we have restricted the domain of our tangent function, it now has an inverse on that interval. We can take that graph, reflect it over the line y equals x, and notice that in doing so, we end up with this shape right here, giving us our graph y equals the arctan of x, or y equals inverse tangent of x. Again, two notations, they mean the exact same thing. Be comfortable with both of them. All right, and one of the cool things here is that our vertical asymptotes of tangent turn into horizontal asymptotes for our inverse tangent function. Okay, there's the graph of y equals the inverse tangent of x. And so our domain is going to be all real numbers. Notice that that corresponds with the range of our tangent function. Our range is going to be from negative pi over 2 to pi over 2. That corresponds to the restricted domain of our original tangent function. Again, we restricted tangent to values of x between pi over 2 and negative pi over 2. That domain becomes the range for inverse tangent. And we say y equals the inverse tangent of x if and only if x is equal to tangent of y. Again, the algebraic proof behind it, we have y equals the tangent of x. That's our original tangent function. If we want to get the inverse of that function, we interchange the roles of x and y. X is equal to the tangent of y. Now we have the inverse. However, we want to solve for y. To solve for y, we need to undo taking the tangent of y. To undo taking the tangent of y, we must take the inverse tangent. The inverse tangent of x is equal to the inverse tangent of the tangent of y. We get the inverse tangent of x is equal to, inverse operations cancel each other out, is equal to y. Y is equal to the inverse tangent of x, and x is equal to the tangent of y. Both of these statements mean the exact same thing. We just like the one where we have y written as a function of x. All right, so there you have it, an introduction into our inverse trig functions. and their definitions. Now, the key thing here, all right, we're not going to be graphing these functions at all. This is probably the last time that you will see these graphs. However, it is important to understand their ranges, okay? In the next video, I'll talk more about the ranges of these functions and how we are going to use them to evaluate inverse trig functions.